Okay, folks, welcome back. Quadratic functions and equations, lesson 2, analyzing quadratic functions, part 1. Lots of information in the next couple of lessons, but hopefully by the end of lesson 2, or the second part of this, it makes significantly more sense. So, quadratic function. Quadratic function is a function which can be written in the form of, as function notation, f of x. Come on, pen, there we go. F of x is equal to ax squared plus bx plus c, or an equation form where it's y equals the same thing. And we've used this form a number of times when we did our factoring in it. And then, of course, these things here where a, b, and c are all real numbers and a cannot equal 0. If a equals 0, then this term is 0 and we end up with a straight line. It's not a quadratic anymore. And a, b, and c have to be real numbers. If they're not real numbers, we can't graph them on our coordinate grid. So those are just little add-ons that we have to put there to make sure that you can do the question. So a quadratic equation is an equation which can be written in this form, ax squared plus bx plus c equals 0. Okay? The roots of the quadratic equation of this, ax squared plus bx plus 0, or plus c is equal to 0, are the zeros of the related quadratic function. So remember, that's what we did in the last lesson, right? We talked about zeros of functions, we talked about roots of equations, we talked about x-intercepts all being the same thing, right? So this still applies. There are two main forms of a quadratic equation that we're going to deal with. One is general form. That's the ax squared plus bx plus c, or whether it's function notation or as an equation. The other form is standard form. A times x minus p squared plus q, and again, in function notation or equation form. With both of these forms, we can get information. And if you remember from the last lesson, this value of c in our general form is our y-intercept. Okay? Our y-intercept, so you can remember that. That's one piece of information. But we can get two different sets of information from both sets or both forms of these equations. There's more information in this one than there is in the general form, but as we work through, you'll see what's available to us. Over the page. Analyzing the graph of the function with the equation y is equal to x squared. We call this form of the equation y equals x squared Joe average parabola. Quadratic functions lead us to parabolic curves. Parabolic curves are U-shaped graphs. Okay? For the purpose of pre-calc 11, we'll only be worried about parabolic curves that open up or open down. When you get into next year, you'll look at parabolic curves that open left and right as well. Okay? But we're only going to be concerned with the ones that open up and down. So we need to have a decent understanding of how we can how we graph this Joe average parabola. So we're going to start with this table of values, and we're simply going to substitute this x value into this equation and square it. Right? So -3 times -3 is +9, and we do that for the rest of the table. -2 times -2 is +4. -1 times -1 is 1, 0 times 0 is 0, 1 times 1 is 1, 2 times 2 is 4, 3 times 3 is 9. Ooh, not 3, 9. That's your Joe average parabola table. It might even be a good idea to remember what 4 would be, as well as -4. Okay. Now, when we graph this, we're going to plot our points, and because I've done this a number of times, I know what the shape is, but we're going to start with -3 and 9, -2 and 4, -1 and 1, 0, 0, 1, 1, 2, 4, 3, 9. So -3 and 9 is right here. 2 4s here. 1 1 is here. 0 0, 1 1, 2 4, 9. And you get a nice U-shaped graph. Now, my pen does not allow me to draw a nice curve, so I'm just going to wing it. Here we go. There we go. Nice U-shaped curve. This is the Joe average parabola. Okay, you should be able to plot this almost instantly on a piece of graph paper. The axis of symmetry is the mirror line which splits the parabola right in half. So if we took a line and we drew it straight down the middle like this, this is going to cut this parabola directly in half. What is the equation of that line? Okay, and hopefully you remember vertical lines have equations x equals some number, and in this case, 0. That is called the x-axis of symmetry equation for this parabola. Whatever line cuts it right in half. And the funny thing is an extra, because we're probably going to get there eventually, is that this x-axis of symmetry value is also the x value of the vertex. What's a vertex, you might ask? Well, a vertex is a fancy word for a corner. A corner in the parabola is that lowest point, or if it goes up the other way, the highest point. The vertex of a parabola, it says it right here, a vertex of a parabola is where the axis of symmetry intersects the parabola. The vertex can represent a minimum point, as in this type. This is a U-shaped graph that opens up, that's going to be a minimum. U-shaped graphs that open down will have a maximum point, okay? Depending on whether or not the parabola opens up or down. Label V the vertex on the graph and state its coordinates. So the vertex is right there. It has coordinates 0, 0. The maximum or minimum value of a quadratic function occurs at the vertex and is represented by the y coordinate of the vertex. Complete the following. Do we have a maximum or a minimum? We have a minimum. Wrong color, purple. Is it purple? Purple. We have a minimum value of the function with the equation y equals x squared. That minimum value is 0. It's the y value of the vertex. State the domain and the range of the function. Okay. So the domain, if you remember, are all possible x values, and the range are all possible y values. Now, if we go back to our graph, if I just blow this up, what are our possible x values? So this is where you ask yourself, can I have a graph? Will this graph touch way out here at x equals 5? Eventually, way up there, it would touch it. And I can continue to go further out, or I can go the other way. But at some point, that line is going to touch that graph. That parabola would eventually get there. If we include all of those values, we simply say the domain x belongs to the set of all real numbers. X, fancy E, R. X belongs to the set of all real numbers. And then what's the range? Well, the range has to do with this minimum, maximum idea. Okay, so that's where we go y. And then if we look back at the graph, what are our possible horizontal lines that we can have? The graph doesn't touch down here, does it? Never will. Or here, or here, or here, until it gets to 0. So that point where that graph touches 0, that's your minimum value. That's the minimum value. And then it's everything above that. So it's all of those numbers as well, going up the y. So that's everything greater than or equal to 0. So this minimum value also belongs there. Oops, the wrong color. 0. And because we have a minimum and it's greater than or equal to, we use our greater than equal to. So a good rule of thumb to remember, if we have a minimum, it's going to be y is greater than equal to some number, whatever that minimum value is. We have a maximum. So a minimum is when our parabola goes like this. Our maximum is a parabola goes like this. Y is going to be less than equal to some number, whatever that maximum value is. Note, the following investigations can be completed as a class lesson or as individual assignment. The process used for these exposures, we don't need to worry about that. Over the page. Analyzing the function with the equation y is equal to a bracket x minus p squared plus q, where a is equal to 1. So each of these parameters, they're called a, p, and q, have a different effect on our parabola. And eventually you're going to know what they are, but I'll give you a quick preview, I guess. The values of p and q, those are going to tell us our vertex coordinates. The x value of our vertex is p, the y value of our vertex is q. We have to be a little bit careful with signage, but that's what we get. From both the x and y values of our vertex, we can get many other things. From the x value, we can get the axis of symmetry. From the y value, we can get our maximum or minimum value. And then, of course, depending on which way it's opening, we would determine whether or not which type of range we're going to use. This a value has two functions. One, it's going to tell us whether or not a graph is longer and skinnier than normal or shorter and fatter than normal. And it's also going to tell us whether it opens up or down. Positive, it's going to open up. Negative, it opens down. But through these investigations, we're going to be exploring that. Okay, so that's a quick preview. The next three investigations help us explore some general transformations on the graph of y is equal to x squared and the relationship they have to the standard form y is equal to a bracket x minus p squared plus q, where a is equal to 1. A transformation is an operation which moves or maps a figure from an original position to a new one. So it transforms it from one spot to the next. Okay? Investigation 1. Analyzing the graph of y is equal to x squared plus q. So in this case, this is actually what it looks like. Y, oops, wrong pen. Y is equal to 1 bracket x plus 0 squared plus q. So there's your standard form with this value being 0. Okay, this value being 0. So what happens when we change our graph a little bit? So we got to take our Joe average parabola graph, which I believe is already graphed for us. There's our Joe average. And then we need to graph f of x plus 3 and f of x minus 3. But f of x is x squared. So this is really y is equal to x squared plus 3. This is y is equal to x squared minus 3. Okay. So there's your equations. And then it says use a graphing calculator to sketch these. So I'm going to go to Desmos. Eventually go to Desmos. Come on. There we go. I'm going to put in my Joe average parabola, y equals x squared. There's Joe average parabola. I'm going to put in y is equal to x squared plus 3. Y is equal to x squared plus 3. Ooh, not 33. 3. What happened to our graph? It moved up 3 spots, didn't it? The shape hasn't changed at all, but it's moved up 3 spots. And then y is equal to x squared. What do you think is going to happen with this graph? Minus 3. Move down 3 spots. So there is our Joe average parabola. Y is equal to x squared, the red line. Y is equal to x plus 3. You can see our graph moves up 3. Y is equal to x minus 3. You can see our graph moves down 3. So now you can see what happens to our graph just by changing that value of q. What does that value of q do? That value of q moves our graph up and down. So we could sketch those graphs on here. I'll do this one. I'll do x plus 3 in red, and then I'll do x minus 3 in blue. Plus 3. 1, 2, 3. 1, 1. 2, 4. Draw your line. Done. And then what did I say this one was? Blue? Blue. Minus 3. 1, 2, 3. 1, 1. 2, 4. There's your parabola. So there's your two parabolas. One moves it up 3, one moves it down 3. Complete the chart. Let's do f of x plus 3. So let's talk about f of x. F of x is equal to x squared, straight up x squared. So it's row average parabola. Our vertex, 0, 0. Our minimum value is 0. The lowest point is 0. Our equation of our x-axis of symmetry is 0, the x value of our vertex. And there's no transformation, which means it doesn't move anywhere. F of x plus 3, our equation. This one was red. Y equals x squared plus 3. What's the vertex of our red graph? Vertex are this point, coordinates of this point, 0, 3. 0, 3. We still have a minimum because it's opening up. That minimum value in this case, though, the x value of our vertex, sorry, I mean the y value of our vertex, minimum 3. Equation of the x-axis of symmetry, x equals the x value of our vertex. You always have to show the equation, x equals something for the equation of the axis of symmetry. And then what happens to our red graph? It's called a vertical translation because it's moving up or down vertically, and it's moving 3 units up. And then our second example was blue. Our equation, y is equal to x minus 3. Our vertex is 0, negative 3. We still have a minimum value, this time of negative 3. The equation of our x-axis of symmetry did not change. We have a vertical translation. T. 3 units down. Okay. So that value of q straight up moves our graph up or down. What does the effect of the parameter q have on the graph? Oh, we didn't do our last line. F of x plus q. Let's go back to purple here. Y is equal to x squared plus q. What do we know about our vertex? 0, q. We have a minimum value of q, and x-axis of symmetry equal to 0. We're going to have a vertical translation of q units. We don't know if it goes up or down, though, because we don't know whether or not q is positive or negative. Okay, what's the effect of the parameter q on the graph of y is equal to x squared plus q? It gives us a vertical translation q units up or down. If it's positive, up. Negative, down. Compared to the graph of y is equal to x squared, the graph of y equals x squared plus q results in a vertical translation shift of q units. If q is greater than 0, the parabola moves up. If it's less than 0, it moves down. Oh, kind of exactly what I just said, hey? Over the page, investigation number 2. Analyzing the graph of y is equal to x minus p squared. And really, again, this is y is equal to 1 bracket x minus p squared plus 0. So remember, this is not going to move up or down anywhere because it's not getting any kind of vertical translation. But again, if we start with f of x being x squared, f of x plus 3 would be y is equal to f, or not f, sorry, bracket x plus 3 all squared. Or y is equal to x minus 3 all squared. And we're going to do the same thing. We're going to put these into Desmos and see how it affects our graph. So here we are again, y equals x squared. And then we have y equals bracket x plus 3 and bracket squared. Ooh, what happened? It moved left 3 spaces. That's a positive 3. And then our third one, y equals bracket x minus 3 bracket squared. Look, the minus 3 one moved right 3 spaces. Okay, that comes from the standard form of the equation. Okay, so I'll talk about that when we go back to the grid, but we'll go back and we'll sketch these on our grid. Oops, wrong one. X plus 3. X plus 3 moved our graph left 3 spaces. 1, 2, 3. So I'm going to do that purple. One goes here. Purple one. And then I'll do the other one in red. X minus 3 will be in red. And it went right 3 spaces. And then we have another chart. Yeah, another chart. So we have the same first line, y equals x squared, vertex 0, 0, minimum, equation of symmetry, no transformation. But f of x plus 3, that's our purple line, which was y equals bracket x plus 3 squared. What happened to our vertex? What's our vertex of our purple line? 3, 0, negative 3, 0. Negative 3, 0. We have a minimum value still, and that minimum value is 0. And our x-axis of symmetry, though, it moved. X equals, what splits this line directly in half? That line right there, x equals negative 3. This is called a horizontal translation. Oh, I'm going to spell it right for you. Three units left. Purple one moved 3 units left, although it has that plus 3 there, right? So really what happens there is that the standard form of this equation, there we go. The standard form of this equation is y equals a bracket x minus p bracket squared plus q. My equation down below is x plus 3 squared. Well, if it's x plus 3, how did minus p become x plus 3? So if I work backwards, then I'm going to put a 3 here and a minus, minus a negative 3, which actually gives me that plus 3. So now you can see that this is where the negative 3 value comes from. So you have to kind of remember it's opposite to what it shows, what it shows in the equation. Or you could rewrite the equation out every time. I'll talk about more about that in class. It'll be easier doing an example there. If I look at x minus 3, my equation is y is equal to x minus 3 squared. This one moved right 3 spaces, so my vertex is 3, 0. I still have a minimum of 0. My x-axis of symmetry, though, again, it moved. See, it moved way over here. X equals 3. X equals 3. Here we have a horizontal translation three units right. And then we can use the p, right? So if f of x minus p, this would be y is equal to x minus p squared. We would have a vertex of p0. We would have a minimum of 0. We have an x-axis symmetry equal to p. And we would have a horizontal translation, p units, left or right, depending on the value of p. Okay, which is what I just said it right here, right? You're going to get a translation, horizontal translation of some kind of p units. And E, compared to the graph of y equals x squared, the graph of y equals x minus p squared results in a horizontal translation. Can't spell horizontal tonight for some reason. Horizontal translation of p units. If p is greater than 0, the parabola moves left. No, oh, sorry, right, I mean. If p is greater than 0, it moves right. If p is less than 0, the parabola moves left. And remember, that comes from rearranging x plus 3, for example, squared, to x minus negative 3. That is less than 0. It's going to move left. Okay, so it's opposite to what it looks like in the actual formula. Over the page, investigation number 3. Well, what happens when we have both of them, both P and Q change? Obviously, we're probably going to get some kind of both vertical and horizontal translation. So question, consider the function y equal f of x is x squared. Write an equation which represents f of x plus 2 minus 4. That equation is going to be, I'm going to go to purple, y equals bracket x plus 2 squared minus 4. Predict the transformations. Use a graphing calculator to verify. So what's going to happen with this graph? This graph is going to move 4 units down. And how many units left or right? 2 units. 2 units. But is it going to be left or right? Remember, this comes from x minus 2 squared. So this is going to be 2 units left because it's negative 2. So let's check that on Desmos. X plus 2 minus 4. Checking this on Desmos, I'm going to go y equals bracket x plus 2 and bracket squared minus 4. Look at that. Our vertex moved 2 units left, 4 units down. Every point on that parabola actually moved to 2 units left, 4 units down. And we'll do some work with moving a parabola around using Joe average parabola. So back to our notes. Our equation, y equals bracket x plus 2 squared minus 4. Our vertex becomes negative 2, 4. No, negative 2, negative 4. Our minimum value changes now, negative 4. Our x-axis of symmetry, x equals negative 2. And we have a translation of 2 units. How do we want to simplify this? We can make it 2. Let's go horizontal translation, 2 units left. And we have a vertical translation, shift 4 units down, which shows us now how we can use the parameters p and q to manipulate our parabola. F of x, x minus p, our equation is going to be y is equal to bracket x minus p squared plus q. Our coordinates of our vertex will be PQ. Our minimum value is Q. Our x-axis of symmetry is P. And then, of course, we're going to have some kind of translation, P units left or right, and Q units up or down. Hopefully you're kind of catching on to that. Let's look at example 1. Describe how the graphs of the following functions relate to the graph of y is equal to x squared. This is x plus 10 all squared, which is really x minus a minus 10 all squared. So this is going to be a horizontal translation, 10 units left. Y is equal to x squared plus 4. Sometimes it's easier when you see that x squared by itself to go x plus 0 squared plus 4. That will help you with figuring out the coordinates of the vertex later. So this is just going to be shifted up. So it's a vertical translation, 4 units up. Question C looks a little bit oddball, doesn't it? We don't have y by itself. Well, we have to get y by itself first. Subtract 8, y is equal to x minus 5 squared minus 8. We're going to have a horizontal translation, 5 units right. We're going to have a vertical translation, 8 units down. Example number 2. The following transformations are applied to y equals x squared. Write the equation of the image function for each. Horizontal translation, 5 units right. So we have y is equal to x minus p squared plus q. We're going left and right, so that's a change in p. It's going right 5 units, so it's got to be positive. So it's x minus 5. Ooh, I almost wrote 8. 5 squared. Nothing happens up or down, so q doesn't exist. So technically plus 0, we don't need to write it. Question B, translation of 6 units down and 4 units left. Well, 6 units down is going to be minus 6. And then 4 left, that's plus 4. So that's x minus a minus 4. Looks kind of like that. But I don't want to have the minus minuses in the brackets. So I need to rewrite that as y equals x plus 4 squared minus 6. And then example 3. Write the coordinates of the image of the point 3, 9 on the graph of y is equal to x squared when a translation of 2 units up and 7 units right is applied. So from 3, 9, if we go 2 units up, does that affect the 9 or the 3? Up and down is y, it affects the 9. So I'm going to go 11 for the y value. And 7 units right. 7 units right from 3 is 10. So I've just moved that point 2 units up and 7 units right. Normally we would talk about left and right first because it is x, and then up and down second because that is y. We always like to talk about coordinate stuff as x, y. Brings us to the end of lesson 2. You'll have to check the board or Scholantis or something for questions. We'll see you next time.